So we've looked at a couple different sequence types already this week. We looked at arrays, which is built-in functionality of the C language. We looked at structs and how we can use arrays and structs to build variable int arrays, where we can have a pushback function, or we can have any number of other functions conceptually, or methods, if we're sort of thinking about this as being object-oriented. But we can have functions that operate on variable int arrays that result in having a different size array. But there's one other common structure that gets used for a sequence data type that's worth talking about. This isn't going to be directly useful for the upcoming homework, but it comes up surprisingly frequently, and we're going to need it in a couple weeks for... we're going to need it a bunch of places. This is something that comes up frequently. And specifically, the data type that I'm talking about is the linked list. So let me go ahead and open up a file, and we're going to create a program. We're going to create a program that is going to sort a list of integers. So I'm going to go ahead and add some headers that we need. And then we're going to define a linked list. Now, if you've done Fundies 1, you remember the definition of a list. A list is one of empty or cons, like some item. I guess we'll have a list of int here, and then list. So we have this this definition where a list is one of two possible things. Talk about this as being a union data type, but one of the things that it could be is a struct, where we're going to construct something with multiple fields. For us, what we're going to do is we're going to define a list as being either null pointer or pointer to int list struct. And I'll call that an int list for the fun of it. But we're going to talk about a int list type. So we need to say struct int list, and if we remember from earlier, we want to say type def struct, so we actually can talk about an int list type rather than a struct int list type. And then we're going to have two fields here. So this is a list of int, so the first thing is going to be the head of the list, and then we're going to talk about the tail of the list, which is an int list pointer, which then, if this is the end of the list, that tail will be null. Otherwise, it's a pointer to another item in the list, and we'll get this sort of sequence of these structures, one for each item in the list. Now, one thing that's sort of funny here is that I have to call this a struct int list pointer. I can't say int list pointer here because the type def isn't done working. So for recursive data types, recursive structures in C, we do have to use this struct whatever form of the type name. So then the operations that we have on a linked list are cons is going to add an item to the front of the list. So that's not pushback. If we were trying to do sort of the equivalent of what we did with our variable int arrays, cons is sort of push front. We have a head and tail operation, but for those we can just access a field. And the other thing that we're going to need here is we need a way to make one. That's cons. Cons is going to actually construct a list in addition to pushing on the front. And so then I'm going to create a free list, which is going to recursively free the list, although we'll find out that there's some complications there. So int list cons int x int list y's. Int list x's. So to create a new cell for a linked list, we call malloc to allocate one more int list structure in a this linked list structure is frequently called a cons cell. So we're going to create one cons cell. We're going to return that new thing that we're doing. And then the tail of the list is going to be the list that we are consing onto. So then, of course, we need our free list. We call malloc here. That means we need to, somewhere in our program, make sure that we call free for every time that we call malloc. We don't call free in this function. Instead, we return the pointer. So that means that the caller of this function is responsible for either freeing the resulting structure or for delegating that responsibility to someone else. And the behavior that we actually want to do here, well, I'll talk about the behavior a little bit more later because it's slightly complicated. So here we're going to take an int list x's, and if that's not null, so one of the possibilities is that we have a null pointer, but if it's not null, then we're going to free the list of x's tail. So this is a recursive operation, and then we're going to free x's. Now, we want to be able to read a list of ints from the user. So we're going to go ahead and write a function that does that. We're going to have the user, or have the interface to this function be that the user is going to specify how many ints to read. So we'll start with an empty list. And we need a local variable y because we're going to use scanf. So we're going to take one int, we're going to read it into that variable y, and then we're going to cons y onto y's. So if we can read a list, we probably want to help our function to print a list. Now we could follow the template from Fundy's one for a list, but in C we have this for loop pattern that lets us avoid recursion, and whether or not we want to avoid recursion depends on exactly how we're thinking about problems. But when we have a nice clean pattern that isn't recursive, that just lets us iterate through something, it's probably a little bit more straightforward to just do that. So we're going to start by assigning this sort of iterator to point to the first cell in the list. If that isn't the end of the list, we're going to go ahead and print the item in that cell. Afterwards, we're going to move the iterator forward to the next cell in the list. And we keep doing that till we hit the end of the list, at which point we're done. So now I'm just going to go ahead. I mean, the next thing that we want to do is create that sort function, since that's what we're doing, but I'm not worried about that yet. I've typed way too much code already without testing this, so sorting, like trying to sort would be crazy before we've proved that we can like read in a list and print it back out. Underscore here indicates that we're not using those variable names. First thing, we're going to ask the user how long the list is, and we're going to read that into NN. Then we're going to have the user type in the integers that they want to read. So x's is going to be the result of calling readInts to read in n ints. Then we want to free list x's and return 0. The other thing that we want to do here is print the list x's. So that's a lot of code. Let's see if we can get that to work. It compiles with no warnings. That's a good thing. All right, simplest case, we want to read one int. It's going to be 5, and it prints back out 5. Beautiful. Let's try 3. How many ints? 3, 10, 20, 30. And it's going to print back those 3 ints. So it is the correct 3 ints, but the ints that it's printing back are 30, 20, 10. So that's a problem. And the reason we're having that problem is because when we construct the list here, building up a list necessarily goes backwards. So the first item that we insert into the list is going to be the last item in the list. Then the next item is going to get put in before that. The next one's going to get put in before that. Let me be more clear. So we start with an empty list. Then we're going to cons on 10. Then we're going to cons on 20. Then we're going to cons on 30. And so the result that we get is a list 30, 20, 10. So if we want to actually have this work out correctly, what we really want to do is we want to reverse our list. So we're going to write a quick function that reverses a list. And reversing a list is actually pretty straightforward because innately rebuilding a list reverses it. For the same reason that we get a backwards list to begin with, if we just iterate through forward and build a list the same way that we did before, we'll get a backwards list. So we'll start with an empty list, and then we'll do a loop. So now, if we do exactly the same thing, 3, 10, 20, 30, we don't actually have to enter them one per line in spite of the instructions. Scanf will happily take any sort of space-separated integers as input. It can tell that as long as we're putting spaces between them or new lines between them, that they're separate numbers. But in any case, we get the numbers in the same order. Just to be completely clear, 77, 321, negative 55, 88, 5. I press enter, it's going to output the same numbers in the same order. So now we need to do insertion sort. Actually, before we do insertion sort, let's go ahead and check one more thing. If we run this under valgrind, and valgrind is something that the upcoming homework is going to be running on your program to make sure that you don't have memory errors. Valgrind is a debugging tool that will show you if you have memory errors. If we valgrind list isort and say 3, 10, 20, 30, we actually get some problems in our execution. Specifically, it says that at exit, we had 48 bytes in 3 blocks still allocated. So our program leaked memory. And the most straightforward way to leak memory is that we called malloc to create some things, and the only thing that we call malloc on is list cells right here. This is the only instance of malloc in the program. And so if we have memory leaks, probably we called malloc here and didn't free it. Now think about this for a second and see if you can figure out where we messed this up. To be entirely clear, let me show another version of this. need to rebuild it. Let me start building with debug symbols, just in case Valgrind wants to give us debug symbols. So the version that reverses it has no memory leaks. All heap blocks were freed, in use at exit 0. So the version that reverses the output, because it doesn't call the reverse function, doesn't have the memory leak. So the problem is because we reverse it. Now, if we look at this in a little bit more detail, what's going on is that we've allocated a list called y's, and then if we say return reverse y's, reverse takes y's as input, but it doesn't free it. It, in fact, allocates a new list. And so what leaks is this original reversed version of the list y's, because from readints we return the reversed list, and that gets freed later. But to fix this, what we need to do is something like int list pointer z's is going to be reverse y's. Then we say free list y's and return z's. And with that version of it, 5, 10, 20, 10, 20, 30. It's going to go ahead and print it out, no memory leaks. So that's one complication. We'll talk about some of the implications of linked lists working this way and programming in C more later, because this is a symptom of a larger problem with what we're doing. But as long as we're very careful about this, this works fine. And lots of C programs are written that use linked lists in this way, where every time you do linked list operations, the result is going to be having made a copy, and you have to make sure that you free all the copies before you exit. So the next thing that we're going to do is this sort function. And the way we're going to sort is with my favorite simple sorting algorithm, and that is insertion sort. So insertion sort is going to return an int list. It's going to be called isort. So we're going to take an int list x's and we're going to return a sorted list. The way we're going to do that is we're going to start with an empty list as our output. And then we are going to, for each item in the input list, just the same iterate through pattern. It doesn't actually matter what order we go through in, as long as we visit each item twice, because for insertion sort, we insert every item into the list in the appropriate place based on the items currently in the list. So we're going to say int list z's is going to be what we get if we do an insert into y's of cur head. And the way we're going to do this is every single insert operation is going to make a copy of the list, and so again we're going to free the previous list. Yes, there's a lot of copying here. No, in most languages where you are working with things like linked lists, you don't have to do this much copying and freeing, but the straightforward way to do it in C results in doing this much copying and freeing. So now we need that insert function. So insert is going to take int list x's and an int x. And what this does is we're going to insert a number into a sorted list. And that precondition is important. X's has to already be a sorted list for this plan to work. But since we're doing all our inserts into a sorted list, it always will be. So if we have an empty list, or if we have a copy, if we have a if the head of the list is greater than the number that we're trying to insert, then we're going to go ahead and return the thing that we get if we insert X at the front of a copy of the list. That means we're going to need a copy list helper. One second, I'll be back. Alright, where were we? I think we were writing this insert function. So the story is we were trying to write a function that, given a list x's, which must already be in sorted order, and an integer x, will return a list, which is the list x's with x inserted in the position such that the result is still a sorted list. So the first case is that we either have an empty list, or the first item in the list is bigger than the item that we're inserting. So that means that we're trying to build a sorted list in ascending order. So if the first item in the list is bigger than the item that we're inserting, then the new item goes on the front. And in that case, we're just going to cons x onto a copy of the list. Now, why do we need to put it onto a copy of the list? You know what? Let's just not do that. That seems too complicated. Else, we're going to go ahead and return the result of consing the head of the list onto what we get if we insert into the tail of the list the value x. So either we create a list. In both cases, we are creating a list. In the first case, we're going to use the list that we're inserting into as the tail. In the second case, we are going to use the result of doing a recursive insert as the tail. So this should produce right answers. Let's see what we get. Oh, we have to sort the list. So let's go ahead and print out our input. Sorted list. So let's say int list y's is going to be isort x's. Let's make sure that the new list that we're getting back from isort also gets freed here. 3 ints. So 20, 10, 30. So it's going to go ahead and print out the input correctly, but then we get a double free detected. Double free detected. So I guess the simplest way we can deal with that double free is we're going to assume that it has something to do with this free list y's that we added, and go ahead and just accept the memory leak, because a memory leak at least isn't an immediate crash, whereas a double free means everything's broken. We have a corrupted heap. We're still going to have to debug to try to get rid of that memory leak, but at least with a memory leak we can see if the logic works. So list sort 3, 20, 10, 30, and now we segfault. Why do we segfault? Well, one of the reasons why we're segfaulting is that we're not printing the sorted list, so let's go ahead and print the sorted list. Well, I mean, one of the reasons why we're segfaulting before we see the sorted list. So let's comment out all our frees, and then go ahead and say 3, 20, 10, 30. So it just is going to go ahead and segfault immediately. It's time to debug! List isort. Run 3, 20, 10, 30. So the problem is at line 27, which is the first line of free list. Cannot access memory address. The problem is free list So what appears to have happened is we appear to have created a circular list, because it's trying to free repeatedly the same value. So my guess is that if we go ahead and look at like frame 17 here, somewhere in the middle, and we print out x's, we're going to discover that X's is a cell at this address, but the tail of that list is also a cell at this address. So this is a mess, and somewhere we've built this circular list which can never be freed, which is sort of a problem. So that's obnoxious. Why are we calling free list? Well, we call free list here in isort. So let's just comment out all our frees until we get something to work, and just see if we can get this to sort even with ridiculous memory leaks. 20, 10, 30. There we go. Once we get rid of all the frees, we're able to successfully have this sort of list, which is good, but we run this with valgrind, and it's going to complain that we lost 128 bytes trying to sort 3 integers, which is 12 bytes of data. So trying to sort 12 bytes of data, we leaked 128 bytes of memory. That's not great. And the basic problem here is a problem of ownership. We have to make sure that for every pointer that we produce, it's very clear who's responsible for freeing what. And with this list structure that we have, each cell in the list potentially has a pointer to another cell in the list, and our free operation is recursive. So if we get into a situation where we have 2 lists, but those lists share some structure. So for example, we have X's is and Emacs broke for some reason. X's is the list 10, and then Y's is the list 20, and then just the list X's by reference. So X's here is just the pointer to the cell with 10 in it. Then we can't actually free both of them. The only way we could safely do this is if we only freed Y's and never freed X's, but then that means every piece of code that we write has to know whether or not we have the sort of most outward list, or whether there's still other references to lists in the middle, and this is basically implausible to deal with manual memory management directly using malloc and free without trickery. Most of the situations where people use these linked list structures are in programming languages with garbage collection, where you can just go ahead and basically write code that in C would be leaking the memory, but once the memory sort of no longer has something referencing it, the runtime system will automatically clean it up. And we may talk a little bit more about garbage collection in a future lecture, but that's not what we're trying to do right now. This is a good example, though, of a situation where garbage collection would help us. But what I want to do here is just make it sure that we never have any of that shared structure. Every time we do anything that might result in producing a new list, if we want to include the data from an existing list in the new list, we're going to include a copy of that data. So we're going to create a function copy list, and I think this is the only place we need it. So copy list, honestly, int list, we could just do 2 reverses and free one of them, but instead we're going to do it this way. So if we have a list, we're going to return a new list with the head of the old list, and then we're going to recursively copy list, the tail of the list. Otherwise, we're going to return empty list because we can. Now let's give that a try and see if that fixed everything. It may not. I put a underscore one too many times here. Okay, that compiles list isort 3, 20, 10, 30. So we have no bugs there, and that is even with all of these free lists that we have uncommented. Let's see if I got this right and whether Valgrind will be happy with us. 20, 10, 30. Yep. We did in fact... I mean, it's saying that we allocated 2k in the process of sorting 3 integers. That may be high, that may include some library usage. But this claim that we had 14 allocs and 14 frees, that may even be true. We may really have done that much memory allocation. We may see later some ways to try to get a little bit more efficiency and allow things like shared structure, which is one of the benefits of a linked list. But for now, we're not going to. That's all I want to cover for this week. Good luck on the upcoming homework, and I will have more lectures for you next week.